the California hills. An epic rematch is about to begin against the backdrop of history and Ronald Reagan's legacy. When it's over, the fight for the nation's highest office won't be the same. Tonight, a debate doubleheader at the Reagan Library. A second chance for voters to compare the candidates side by side. If you thought round one was intense, you haven't seen anything yet.
Welcome to the 2016 presidential debate. I am Meng Yang, your moderator this evening. Let's meet our candidates for tonight. We have Jacob. We have Rush Lumber.
I'm Rush Lumber.
And we have Douglas Fur. Thank you for being here, gentlemen. The unemployment rate in the United States may be increasing, but we have much more work that needs to be done. So Jacob, how would you determine whether a composite beam fabricated with lag screw and wood glue would be a viable substitute for a standard timber beam?
Excuse me? I'm sorry, I don't quite understand the question.
I'm sorry, Jacob. Time's up. Same question, Mr. Lumber.
That's an excellent question, Meng. In order to determine this, I would recommend the following. First of all, standard beam and composite beam specimens must be acquired. For this particular experiment, I would recommend using a 2x8 Douglas fir beam, 36 inches long, for the control beam. The composite beam should be constructed out of 2x4 Douglas fir beams, also 36 inches long. The composite should be fabricated using wood glue and 6-inch lag screws. A flexural test should then be conducted on the two beams using a load applying test machine. A point load should then be applied at the center of the beam. An LVDT deflection gauge should be attached to the measured deflection. The deflection's maximum load, failure modes, and stiffness should then be compared in order to determine whether the composite beam is a viable option. Of course, the standard beam will only be 1.5 inches by 7.5 inches and 1.5 inches by 7 inches for the composite, but the test will be effective nonetheless.
Wait a sec, I think he had more time than I had. If you...
Jacob, please do not interrupt. Mr. Fur, do you have anything to add?
I actually have to agree with Mr. Lumber on the experiment, except for a few minor details. Due to the high force this beam will surely stand before a flexural failure, I would highly recommend the use of a bearing plate to distribute the load over the beam. Otherwise, the beam will fail under a crushing force and not meet the experimental objective.
Thank you, Mr. Fur. Now, Jacob, the tension is rising in Syria. There is a discussion whether the Syrian immigrants should be allowed into the United States. So what type of predictions would you have for a standard 2x8 beam?
The Syrian immigrants is definitely a concern for the United States. What about a beam? What was the question?
Jacob, I'm sorry, but you're out of time. Same question, Mr. Lumber.
I'm glad you asked that question. Let's run some of the numbers. Utilizing the bending stress equation and the tabulated modulus of rupture value from the Wood Handbook, we can calculate the maximum moment. Using shear moment diagrams, we can relate the maximum load applied to the maximum moment. This will then give us the load for a flexural failure, 11.02 kips. To determine the maximum load for a shear failure, we can utilize the Wood Handbook's value for shear parallel to the grain and the equation that relates maximum shear to shear stress in order to find the maximum load before shear failure, 12.6 kips. By the definition of stiffness, applied load P equals stiffness constant K times deflection X. If we substitute the equation for maximum deflection into this equation, the values for the applied load cancel, leaving us with stiffness equals 48 times the modulus of elasticity times the moment of inertia divided by the length of the beam cubed, thus giving us a predicted stiffness value of 8.6 kip per inch. With these values, I predict a flexural failure.
Mr. Fur, same question, but now referring to the composite beam.
That's a great question, May. I must admit, Mr. Lumber's calculations are well proposed. For the proposed composite beam, the calculations will nearly be identical, only changing the height of the beam to 7 inches from 7.5. Therefore, the predicted flexural failure load will be 11.02 kips. The shear failure will be 12.6 kips, and the stiffness will be 8.6 kips per inches. From these calculations, I predict a flexural failure mode.
Thank you, gentlemen. Now, I assume that you all brought your test results from the experiment that you performed. Jacob, what can you conclude from the objective posed at the beginning of the debate?
Wood beams are good, I guess.
Well put, Jacob. Mr. Lumber?
After the experiment, it was discovered that the standard beam's maximum applied load for failure was 8.895 kips. And unfortunately, the beam did not fail flexurally, but was actually a bearing failure. The ends of the beam were crushed, leading to the formation of horizontal cracks from the end of the beam. You know, I think I do. I have the standard beam after failure right here. The cracks began at the end, at this point right here, and before a sudden crack came through the length of the beam. From the data, the stiffness coefficient of the standard beam came out to be 22.64, which was significantly lower than our predicted value. However, the test was not performed ideally. The experimental deflection value used to calculate the stiffness coefficient of the beam was significantly larger due to the fact that the beam was exhibiting pressure. These inaccurate results produce an inaccurate stiffness value. Therefore, the max deflection value from the experiment, 0.931 inches, cannot be used as dependable data either, unfortunately.
Mr. Furr, same question, but for the composite beam.
The composite beam withstood a maximum load of 9.593 kips, which compared to the predicted value of 11.02 kips is notably lower. However, based upon Mr. Lumber's discussion, we know that the composite beam handled a higher maximum load than the standard beam. This tells us that, in terms of the maximum load, the composite beam adequately serves as an alternative to the standard beam. When we look at the stiffness constant for the composite beam, we can reach the conclusion that the composite beam is more stiff than the standard beam. This is realized by comparing the stiffness coefficients. The K value for the standard beam, based upon experimental data and calculations, is 22.64 kips per inch. Comparatively, the K value for the composite beam, based upon experimental data and calculations, is 30.23 kips per inch. Again, this reinforces the idea that a composite beam serves as a viable substitute because it has a greater stiffness coefficient than the standard beam. Furthermore, Mr. Lumber noted that the failure mode for the standard beam was a bearing failure. The experimental failure mode for the standard beam was different than what was actually predicted, which is untrue for the composite beam. The failure mode for the composite beam was flexural failure, and this is consistent with what was predicted for the failure mode. Therefore, although the failure modes were not the same, we can recommend that engineers utilize a composite wood beam if they wish to apply a flexural failure. In fact, I happen to have the composite beam that was tested with me. If we examine this beam, we can see that there are cracks on the bottom near the midspan right here. This demonstrates that the failure happened within the area of the maximum moment, and we know from the predictions and results that a flexural failure mode is dependable. Ultimately, as the future President of the United States, I believe that the composite wood beam is a viable substitute for the standard beam for the following reasons. The first is that it can handle a higher maximum load. The second is that it has a higher stiffness coefficient, and finally, it has a dependable and if not serendipitous failure mode within the flexure area.
Jacob, did you have anything to say about the Great American Lumber Test?
You know what? I sure do. Nobody's yet explained something that myself and many of my fellow Americans hold dear. I speak, of course, of the crushing that occurred at the ends and at the center top of the wood beam. As you can see in this photograph over here, the crushing that happened on the ends of the 2x8 beam did not happen on the composite beam. I propose that this crushing happened because, in fact, the wood grains of the 2x8 beam were oriented perpendicular to the grains of the composite beam. As you can see in this photograph, the The grains of the 2x8 beam were aligned perpendicular to the loads and the support, leading to crushing in between each of the wood grains. The composite beam, on the other hand, had its wood grains aligned parallel to the support and load. This could very well explain the drastic difference in the crushing behavior between these beams.
Wow, I did not expect this kind of analysis from you. This almost makes up for your performance earlier.
Thanks.
All right, folks, this concludes it for our debate tonight. You all get a final remark.
My fellow Americans, a vote for me is a vote for a real politician and not some dang engineers talking about flexural wood beam tests all the time. Thank you and good night.
My name is Douglas Furr, and in 2016, vote for me to become the President of the United States. A vote for Douglas Furr is a vote for practically used composite wood beams that are better than standard beams. Thank you.
I'm Rush Lumber. A vote for me is a vote for the 2x8 standard beam. Thank you.